some revision for test 1. And also don't forget to fill the declaration form or online form for test 1. Just want to verify to everyone. Can you hear my voice clearly? Hello? Can everyone listen to me? Okay, right. So again, we continue this class today. Yesterday we have stopped at our class on the discussion of active transducer. Okay. So today we're going to continue. We're going to look into the concept of passive transducer. So passive transducer is also commonly known as modulator. Okay. And passive transducer require at least an external power source for power conversion. Okay. The example are potentiometer. So you have done in a laboratory exercise using potentiometer, but the purpose of the experiment was how to use the analog and digital uh, instrument to measure voltage and current and also resistance. But basically, meter is a passive transducer which converts a rotary movement or the rotary displacement to electrical signal indirectly. So it means that the rotation is in a relationship with the resistance change, but in order to transform that resistance change into electrical signal, we have to connect the potentiometer to a electrical circuit. So the simplest one is by using a voltage divider. Then we have strain gauge. Strain gauge, we will look into uh, the concept of strain gauge later in the class. So strain gauge is basically a device which converts force into electrical signal. Same uh, like potentiometer, it is a passive transducer. So meaning that we have to apply power supply and also thermistor. Thermistor is a uh, one of the term temperature measuring devices. Okay. The mister, as you can see in the picture, it looks like a common capacitor, ceramic capacitor. So the mister is comparatively small in size, okay, and usually can be found in electronic devices like your laptop, okay, or your smartphone. So they are thermistor. So they can be very small as uh, a bit mean bit size, B-A-D, bit size. And also we have resistant thermal. This is thermal, basically thermal. No, temperature. And the correct temperature. Temp, resistant temperature detector, the RTD. So we're going to look into that later in our class. Variable capacitance gauge, okay, based on the capacitance. Okay. So the variation of capacitance value determine the output of this device. And also we have linear variable differential transformer or LVDT. So LVDT is a type of electrical transformer, okay, as you can see from this figure, used for measuring linear displacement. Okay. The counterpart of the device is called rotary variable differential transformer. So LVDT is used to measure linear displacement. Okay. Linear displacement, for example, uh, from the vertical, sorry, for horizontal axis. So, so we want to measure the displacement on the vertical axis. Okay, so basically we connect the moving part of the LVDT to the object. Okay, object. So we have an object. Okay, and we connect that object to the moving part of the LVDT. So we will look into the advantage, the principle, okay, how what constitutes the LVDT, the advantage and then the disadvantage later in the class. So as like a LVDT, to operate an LVDT, we have to apply a power source. Okay, so like a normal or regular transformer, so the basic principle, the operating principle rely on the power supply that is connected to the device. Okay. Then now we go into the concept into the temperature transducer. Temperature temperature is the most one of the most common parameter measured in the industry. Okay, and also we have seen the pervasive application of temperature nowadays at the moment where temperature is used to measure to detect the symptom, okay, of COVID-19. Okay, so the device they are using can have many type. Okay, so by chance I also have a, for example, I have here, okay, is a infrared thermometer device which can measure, okay, temperature. So this device basically have a laser to focus the direction of the object that one want to measure. So this device basically can measure, okay, the temperature or of an object without having to having a direct contact to the object. So this is based on the infrared radiation. Okay. But then in industry there are many types, and there are many basically the type of temperature sensors or transducer depend on the level of temperature we want to measure. So usually the measuring unit of temperature is in degrees Celsius, or in few country like in the US, they are they are measuring the temperature using the Kelvin unit, degree Fahrenheit. So you need to use some conversion to measure in degree Fahrenheit. But in most of the world, we are adopting the international unit, IS, International Standard Unit, or IS unit. So basically, we are using the degree Celsius. Um, so in this class, we will look into the three type of temperature transducers, which are thermocouple, resistant temperature detector, and also thermistor. So we will look into this. Okay, we will look into this type of temperature transducer. And the principle basically the change of the device parameter depends on the change of measured temperature. Okay, we will look into the difference, the principal difference between uh, the listed transducer in this topic. And like I said, okay, this is one of the most widely measured parameter that in the industry. Okay, so for example, in the food industry, the frying, or in the other food making like bread, okay, and also other food type, okay, like cheese, like beverages. So all depend on temperature measurement. So they want to have that exact quality of food. They need to control the temperature at a certain level and period of time. So it is one of the very important parameter. And also in wastewater treatment. So wastewater treatment is very important to adjust or maintain the temperature of the wastewater at that. So there are many processes in the wastewater. Okay, they have the preliminary tank, the mixing, and then they have the aeration, they have the pH control part, and so on. So those different process, the processes have to be the temperature must be maintained at a certain level. And also in steel manufacturing industry, where the temperature must be hot enough to melt the metal, okay, and it must be maintained before we put the molten steel into the cast to make to mold into a cast to mold into a certain shape. Okay, so let's quickly see into the concept of thermocouple. It is basically a phenomenon or a concept which has been discovered by a physicist, okay, called as Thomas Seebeck back in 1982, where this scientist, uh, what he did was he combined, he used two pieces of wire, and then combine the wire at the end by twisting at the end, and then he heat up the combined end. Then he noticed there is a EMF generated, okay, at the open terminal. Okay, so basically the concept, if we have two dissimilar wire, two dissimilar wire mean two different type of wire, or metal wire. So this metal wire can be a pure form or can be in alloy form. And so we connect that wires at both ends to make two junction, and then we heat it up. One junction we keep at a reference, and another wire we heat it up or we expose to the uh, air environment or body that we want to measure the temperature. So the difference temperature between the measuring junction and the reference junction is proportional to the EMF produced at the terminal, the open terminal. So this is called as the Seebeck effect. Okay. As time goes by, so the based on this principle, the device is then re I mean the device is then is redefined, okay, refined into an industrial form. Okay. So it is used to measure the temperature in the industry. Uh, so this is an example where we have two dissimilar wire. Okay, this is wire A, okay, and this is wire B. So we combine. So so basically we have two dissimilar type of wire. Okay, one type. Let me draw that. So we have one wire. Let's say this is type B. Then we combine this wire with another type of wire. Let's say we call it, so this is type B. Okay. So we make a two junction. So this will be the first junction. Okay. Let's say this is first junction, and this will be the second junction. Okay. This is the open terminal where we measure the voltage. Okay. The voltage. Okay. So how it works, we have two junctions. One junction is usually uh, we keep it at reference. So you can choose this one as a reference. So let's say we maintain this at 25 degree Celsius. So that is the room temperature. So we maintain. So we put the insulation here. So we keep this junction to reference, and the second junction will be the measuring junction. So this junction will be exposed to the object or environment, will be put into the material that we want to measure the temperature. So usually this metal is put into a hard casing here, hard casing, okay, like what we saw here, what we can see here, we put in a casing, casing where the casing is made of stainless steel, for example. So the magnitude or the value, the output value, okay, the output value, the level of the output value of the device of thermocouple, it depend on the metal in use. Okay. Uh, the- in general, the magnitude, okay, will increase linearly. It will increase linearly, but the magnitude, or what in another term, the sensitivity, okay, the sensitivity of the device will be depend on the type, okay, type of metal used. Okay, so I have explained how we use two dissimilar metal uh, alloy combination to complete a circuit, and then how we measure the voltage at the open terminal. Okay, then we can measure the output voltage from that open terminal. But in the last or yesterday lecture, the thermocouple is categorized as an active uh, transducer. So one of the key criteria of active transducer, it does not require any power supply. It generates the generation of EMF is depend on the change of the input parameter. Okay, so you notice there is no power supply involved to operate the thermocouple. But and also another thing is that uh, the increase in temperature, okay, mean will cause a very small increase of the voltage. Okay. So normally sensitivity, okay, the sensitivity of a thermocouple is between 1 to 70 microwatt per degree Celsius. Microwatt is very small. Okay. So if you take that in millivolt, that will be 0.07 maximum microwatt per Celsius. So normally to operate a thermocouple, okay, we need a signal conditioning circuit. Okay, signal conditioning circuit where we have to amplify uh, the output before we can get a meaningful reading. Okay. Otherwise, the signal is very small, the output signal is small, and sometimes we cannot get a great or good measurement due to the small output fuse with noise. Okay, so remember in the past lecture we have discussed about noise. Okay, these are the type. This industrial standard of thermocouple type. The denomination like D, E, G, K, and R, S, T. Okay, so this type, okay, the name is given based on the composition of material. Okay, for example, for type B, it is a combination of metal type platinum with alloy 30% rhodium. Okay. E, combination of chromal with constantan. J, iron with constantan. K, chromal with alumel. And corrosive with methyl. R, basically the combination of platinum and rhodium at different level at 13%. S is 10%. And T is copper with constantan. Uh, so why does it matter having a different composition of material? So the answer is that having a different composition of material, so we can have different range of temperature measurement. So for example, for type B, we can measure temperature, okay, between 100 degrees Celsius and 1.8 kilo degrees Celsius, so 1800 degrees Celsius. Other type, okay, as you can see, has a bigger span, okay, bigger span, like for example, from alumel, okay, it can reach, okay, uh, from negative 700 degrees Celsius to 1200 degrees Celsius. Okay, so that, but not, I think the most popular is like A, K, T. Okay, those are the common type is used in the industry. But basically, it depends on the requirement. Okay, the requirement of your application. Okay, for example, your application need to measure very low device, or sorry, very low temperature. So like, okay, you can, let's say you want to measure like 800, negative 800 degrees Celsius, so you have to go for 10S. Okay, 10S. So this is the comparison, the output comparison, okay, between different type of thermocouple. Uh, so this chart shows the EMF, or the voltage output, versus the temperature in a degree Fahrenheit. So they are tabulated. The output, the comparison. You can see the comparison between the thermocouple is shown in this graph in terms of the response. Okay, so you can see this response start at 32 degree Fahrenheit. I think that is around 0 degrees Celsius. Okay, basically, remember that this temperature is not the temperature of the not the temperature of the environment or the object that we want to measure. This temperature is basically the temperature difference T1 minus T2. Okay, T1 is the temperature of the object. T2 is the reference. Remember that we have two junction. Okay, the first junction will be the measurement junction, and T2 is the reference junction. Okay, reference junction. Uh, so T1 minus T2. Okay. EMF is the output, okay, the voltage output. So you can see the output is in millivolts. So the highest point for a thermocouple transducer can provide is around 60 to 64, 66, around 66 millivolts. Okay, 66 millivolts. So you can see, okay, uh, the difference, okay, of response here. We can compare the sensitivity. Okay, remember the sensitivity in chapter 1. Sensitivity is the change of output divided by the change of input. Okay, in this case, the change of output is voltage. Okay, the voltage delta divided by delta T. Okay. So for example, okay, if we look into this, type K is the moderate type. Okay, moderate type means that it has the middle range, okay, of sensitivity. So how do we can measure the sensitivity? We have to measure the slope. Okay, basically find the slope. So let's say this is so delta, this is around 42. 80, this is 42 millivolt, and this is around 20, 22, 20, 24. Okay, 24. Okay. So delta V will be equivalent to 42 minus 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 24. Okay. Divide by delta T. So delta T here, okay, this is around 1200, 1068, 1800, and this is okay, roughly around one, maybe I would say 10, 1100, roughly. So delta T here is 1800 minus 11000 0 0. I write it down here again. So delta V is 42 minus 24 divided by 10800 minus 1100. So this is in millivolts, this is in degree Fahrenheit. So if we calculate, how much is that? Four two minus 24 doesn't make sense. Minus it is around, so I get is around around 57 microvolt per degree Fahrenheit. 57. So you can correct me if I'm wrong. So basically sensitivity we can calculate from the slope. Okay, the slope. So it shows us the output of the sensor can give at the degree change. For example, 1 degree Fahrenheit change. Okay, so it gives us 57 microvolts. So this is type K is the middle range. Okay, you can see type K is the middle range. Okay. And type B, S, R, and then other type, this is the lower range. T, J, E are the higher range in terms of sensitivity. Okay. What does it means is that for example, if we compare K and E, E give it has a higher sensitivity as compared to the other and also as compared to K. So at any point of temperature difference, like for example at 100 degrees Celsius, 100 degrees Celsius, type E will produce higher output voltage. For example, type K, if the temperature change is around 1000 degree Fahrenheit, so the output is around 20 millivolt. But type E is around 40 millivolt, so double the output. So type E has higher output. Okay, but that is one point of view if you look into the sensitivity. But if you look into the range, okay, the range means the time, the temperature limit, okay, of the thermocouple. So we look at, for example, type tungsten 5%, okay, and rhenium and tungsten 25% rhenium. So the output can reach, okay, the temperature difference allowable or can be measured, can reach up to more than 44,000 degrees Celsius. Whereas for type E, the maximum is only I think it's around 1,600 degrees Celsius, Fahrenheit. Okay? So there we can see the performance. Okay, this can be a good table or graph that can can be used to determine the suitable type of the thermocouple that we want to use for different type of application. Okay, so this is the details. Okay, the details of the popular thermocouple type. Okay, for example, type K is a general purpose, is widely used in the industry due to the low cost. Okay, low cost, and also it is availability. So it can be easily available, and the temperature range can measure between negative 700 degrees Celsius and 1200 degrees Celsius. The sensitivity is around 41 microvolt. Type K, even is that K, yeah, so I calculate 45, maybe slightly this is close. Okay, so that is the medium range. Okay, the medium range. Okay. Type E has a higher sensitivity. Okay, oh, sorry. So this is the measurement in degree Fahrenheit. Okay. Of course, it is different because this is in degree Fahrenheit. So this is the sensitivity in uh, degree Celsius. Okay. Type E is a highest sensitivity. You can see from the graph, E is the graph is the highest sensitivity, around 68 microvolt per degree Celsius. Okay. But the temperature measurement is middle range. So it is very suitable for cryogenic application. Okay. And then we have other J, T, and can read from the slide the details of the type of thermocouple. Okay, so the formula of the EMF is can be constituted by this equation. Okay, E is equal to C T1 minus T2 plus K T1 square minus T2 square. Okay, so what that show here? Okay, show here this part of the equation. Okay, this part equation show us the linear part, linear part, and this part show us the non non-linear part. Okay, non-linear part. Okay, I'll show you the previous slide. So as you can see, for example, okay, this type uh, this tungsten 5% rhenium. So you can see at the beginning, okay, the EMF increase linearly, but as it go higher at the temperature difference, the non-linear response start to appear, as you can see. Okay, so the output, the response will start to be non-linear. Okay. Also, let that this type B, if here between here 32 to 1600 degree Fahrenheit, the output is still linear, but as you go higher, the temperature difference, the non-linearity start to appear, okay, from the output. So, so it can be shown by this equation. So this equation at the low range, as long as this equation at the low temperature difference T1 minus T2, so the linear part will be more dominant. But at higher temperature difference, the non-linear effect will start to appear. Okay? So T1 is the temperature of the hot junction of the measuring point, and T2 is the temperature of the cold junction or the reference junction. So look at this example. Okay. So this example shows the experiment where a copper constant thermocouple sorry, with the uh, constant of C and K. C is 3.75 times 10 to the power of negative 2 millivolt per degree Celsius, and K is 4.5 times 10 to the power of negative 3. Okay? So if T1 is the hot junction or the measuring point is 100 Celsius, and the cold junction is kept in ice, compute the resultant electromagnetic force. We have to draw it. We have to draw the, so it will be something like this. Plus minus T. Okay. This is T1, the hot junction, and this is T2, or the reference junction. So this reference junction T2 is basically kept in ice. Okay, at 0 degrees Celsius. Ice. Okay, so it kept in ice. So we just quickly apply the equation. Okay, equation. So this is K. So this is C. Okay, C. So this is T1. So this is T2. And this is K. And this is T1 square. And this is T2 square. So we get this output, okay, EMF for this question. Okay, before we go there, I want to share you let's look into this question. Okay, this question, a thermocouple was found. So thermocouple was found to have linear calibration between 0 degrees Celsius and 400 degrees Celsius at a maximum temperature. Okay, so this shows the characteristic, okay, of the temperature thermocouple. Okay. So this is the response when the junction, okay, the junction is at 0 degrees Celsius. Okay. But when but when the reference point or the reference junction is changed from 0 degrees Celsius to 25 degrees Celsius, so as you can see, there is an offset in of the characteristic. Okay, the characteristic, this is the original characteristic. Okay, 0 to 25. Okay, then there is the reference junction changed to 25 degrees Celsius, causing an offset. So this offset, okay, shows that when there is no temperature difference, okay, between the reference and the measuring junction or the hot junction, there will be a default value. So default output EMF is called as the correction. Okay. So the question is that determine the correction which must be made to the indicated EMF. The cold junction is at 25 degrees Celsius. Okay. So meaning that you have to find what is the value of the torque. So maybe I will try to show you the answer by using the camera. If you can it's the same thing. You can try. You can you can view from my video. Okay. full screen the not sure how to full screen the camera. Maybe I can stop the sharing. How do I set share content screen? How do okay, now I got it. So, yes. So we have a thermocouple. Okay. Let me draw the thermocouple. Okay. Hang on, let me use some. So we have a thermocouple with different. Okay. So the for the question that we have the output. I'm going to share you the question later. So this thermocouple, this is the P1 measuring what we call as the hot junction. Okay. And here we have the reference junction. Okay. T2. So when T2 is set as 0 degrees Celsius, we get a particular uh, response. Okay, like this. Okay, degrees Celsius, 25 degrees Celsius, 60 volts, so 20.68 millivolts. this is when the T2 at 0 degree Celsius. Okay, 0 degree Celsius. But when T2 change from 0 degree Celsius to 25 degree Celsius, okay, the reference junction, okay, change from 0 to 25, so we get a new response, with an offset. Okay, there is an offset. Sensitivity remain the same, but there is an offset. Okay, there is an offset. So we need to calculate what is the correction, okay, the correction voltage or equal. So mean that if we apply T2 with the reference junction, we must uh, include or put into account the value of E correction. Okay? So how to find the E correction? So we can, I think you get the figure. So it can be calculated by, okay, you see, though there is an offset, okay, both response have the same sensitivity. Okay, sensitivity. So we need to know what is the sensitivity. Okay, we know this is sorry, this is about 400. This point is about 400. Okay, this point is about 20. Uh, so how we can calculate the sensitivity? Okay, we can take from the uh, origin. Okay, origin meaning 0. So sensitivity of the thermocouple, okay, sensitivity equal to delta V over delta T. So this is going to be our delta V. Okay. So over delta V, okay, V2 minus V1 divide by, you can see T2 minus T1. But this is confusing. Don't use this term. Okay, it's a different point. Okay. So we take that 20.68 minus 0 divided by 400 minus 0. Okay. So we get that the sensitivity is 0.0517 millivolts. Okay, so that is sensitivity. Okay. So the sensitivity is 0.057 millivolt per degree Celsius. So that is sensitivity. Okay. So now we get the sensitivity. So since we get the sensitivity, we can estimate ECOM. So since the thermocouple is calibrated at the reference junction of 0 degrees Celsius and is being used at 25 degrees Celsius. So then the correction which must be made, okay, okay. So we want to find E core, okay. So we can use this formula, okay. So we can use this as equivalent. We take the found E core, okay, divided by where is the, the temperature, okay, between 0 to 10, okay, the difference, okay. So E core is 25, okay, minus 0, okay. So we get that E core is equal to 0.057 multiplied with 25, so we get 1.293 millivolts. So that is the correction value that we must, okay. It's too blurry for you, or okay, it's okay. I hope that if I upload this, it can be much clearer. But don't worry, I will share you the answer in the class. I mean, with you, the answer with you later. Right? See anything? Yeah, it's okay. We try other approach. Okay, we try other approach. Okay, I will try to put the question on the slide. Let me lock. Okay, let's do some revision. Let's see what we have here. Let me put in this slide. Okay. Now is the time of trying everything that we can get our hand to. Of course, me adjust something. Okay, let's do some revision for your test. In this question, in centimeter gram second electrostatic unit CGS-ESU, the dimension of force is bracket MLT to the power of negative 2. Okay? And work is M multiplied with L to the power of 2, okay? T to the power of 2, where M, L, and T represent mass, length and time respectively. Okay? So find the dimension of the following parameter in CGS ESU. Okay, first we have to find the charge. Okay, to find the charge, we have to uh, recall the equation of Coulomb's law. Okay, Coulomb's law. So this equation you have to memorize. There's no option. You have to memorize the equation. Okay, so for number one, the equation for okay, the equation for charge, Coulomb's law, F, the force, okay, uh, between two charge. Okay, remember, between two charge, okay, is proportional to the value of the charge between the charge Q1 multiplied with Q2, and also inversely proportional way to the uh, constant, permittivity constant, okay, and also inversely proportional to the distance. Remember, distance between the charge. Okay, we have to charge Q1, we have charge Q2. So we have the distance D. Okay, depending on the value, okay, if they are the same sign or the same positive sign or negative sign, so they have the same charge sign, so the force is repelling, so they are basically pushing each other away. Okay? But this question you have to memorize. Okay? Force is given, force is here, and always remember to use the bracket. Okay? I like to remind you to use the bracket. So otherwise, if you don't use the bracket, so basically we are not using uh, the dimension analysis. Okay? We use the bracket. F is M L T negative 2. Okay? Q, okay, they have the same charge, and then we use charge unit Q plus Q multiplied with Q, so we have square. Okay? And so epsilon is a constant, and D is distant. Okay? Distant. So distance and length are the same. I mean, they have the same uh, symbol of dimension or the same dimension, which is L. Okay. So basically, they are measuring the difference from one point to another point. Same as length. Length is basically measuring uh, all height of object. So length. So they have the same dimension, which is L. Okay. So D is the distance. The dimension will be L square. Okay. So the idea is to get Q. We arrange. You can figure out how to rearrange. So we get Q. Okay, Q. Remember Q. Oops. This is dimension analysis. Q is okay, bracket equivalent to okay, finally you get M to the power of half epsilon to the power of negative 1 over 2 half L to the power of 2 and t to the power of negative 1. So that is basically the answer. Okay. Number two, capacitance. Okay, capacitance. I think capacitance you can find from C. Okay, capacitance. We have to memorize the equation. Okay, capacitance is equivalent to charge over EMF. Q over E or Q over E. Okay, but first to find to find the capacitance, you need to find EMF. Okay? And then to find EMF, E, okay, you have to memorize to know the equation. E is equivalent to number of work done divided by the total of charge that flow. Okay? So you have to know the equation of EMF. Okay? Work is given. Work is given here at the top. So work is here. The dimension for work is given. The total dimension of work is given. So we need to find E and Q is we calculate from the above question. Okay. So W is M L square T negative 2 P negative 2. Okay. From here, that work. Divide by from here. So epsilon negative 1 over 2 and 1 over 2 and 1 over 2 P minus 1. So, so we get P is epsilon negative 1 over 2 and power of 1 over 2 and to the power of 1 over 2 P to the power of negative 1. Right. So, so now we know the dimension of EMF, so we can apply that into this equation. Okay. So you can apply to this equation. I think skip to the answer, so you will get epsilon L. So you should get epsilon L. Okay. The third question is find the resistance. So we can skip it. Find the resistance. So to find the resistance, okay, of course, you have to memorize. Okay, you can use this equation, or you can find other option equation that you can you think you can tackle, like E is equivalent to V R. Okay. So R is our P. To find P power, okay, you can find from work. Okay. What is power? Power is the rate of work, isn't it? P. So P is basically equivalent to W over T. Right? The rate of work. Right? Mistaken. Power is basically the rate of work. Okay. So of course, okay, you can tackle this answer from this equation, and also you can find the answer from this equation. Okay, let's say we use this equation R over E over I. So E, the voltage or the EMF, you already know from here, get the answer, but you need to know what is current. Remember, what is the definition of current? Current is the rate of charge that flow from in a closed circuit. Okay, in a closed circuit. Okay. I is Q over T. So basically just okay, Q over T. T, the dimension is T is time. The dimension is T. Okay. Q is from here. Okay. So Q is from here. Q. So I dimension. So I dimension will be basically this. I write it here. I get the answer in and so epsilon negative 1 over 2 and 1 over 2 L 1 over 2 1 over 2 1 over 2 T negative 2 T to the power of negative 2. So now we have I. So all we need is to find R. So R. So finally we get E here epsilon to the power of negative 1 over 2 and to the power 1 over 2 L 1 over 2 T minus 1 divide epsilon negative 1 over 2 and 1 over 2 and 1 over 2 T negative 2. Is that correct? I think this is not negative. T. This is not negative. Sorry. This is supposed to be positive. Right? So R we get epsilon power of negative negative 1 L negative 1 T. That's the final answer. Okay. Let me look. We have some time. Okay, maybe we can look. Okay, maybe you can look into this question. It's a concept of question. Uh, in measurement, there are some terms that commonly used. Give a brief explanation regarding grief. So provide with sketch of a graph. So this is the answer you can find from your notes. So basically, grief is a slow change of a meteorological characteristic. Okay? So this is a example. Example. So this is a common grief of a instrument. Okay, let's say we have an instrument that we set to measure current at, at a point, okay, and then we set a different time in the future, okay, to see the output, okay, of the instrument. Okay, so we have I mean the current we set from the source. We set the value from the source. Let's say from power supply. So we set the power supply. So those uh, supply power supply we can assume it as a calibration device. Then we notice that the device at at one point in the futures the output start to reduce. Although the current source is set the same as the previous. So we can see the output start to go down. So in this example, we put hour. It's okay. You can put days or you can put year. That is okay. So it shows us the device start to deviate. The output start from deviate from the actual output. So this is due to the internal condition of the device, or maybe due to the component wear and tear. Okay. Then the next question is about uncertainty. What is uncertainty? Uncertainty, this is the by definition and by definition. So you have to memorize. Okay, there is a the other term of uncertainty or the other term accepted is like parameter associated with the result of a measurement that characterize the dispersion of the value that could easily be attributed to the measurer. Okay, or the level of confidence that it obtains. Okay. Standard uncertainty of the result expressed by a standard deviation. One thing for sure is what is the difference between uncertainty and error. So basically, error of measurement is a subset of uncertainty. Okay, it's a subset. So error contribute to uncertainty. Okay? So uncertainty basically is a overall indicator of a accuracy of a device or the state of the device. Okay? So it also they reflect the error reflect the accuracy, reflect the other characteristic, and then uncertainty can be calculated from statistical method. Okay? Although or we can calculate the uncertainty from the nominal value of uncertainty of each component of the device. Okay, we have a circuit. The device have a certain circuit. So each circuit, that for example, is as an op amp or yes a resistor or capacitor, inductor. So we can estimate. Okay, we can derive the equation of the output. Let's say the device is basically measuring the voltage. So we calculate the output equation of the device. So from that output equation, we can estimate each uncertainty of the device. So we can estimate using the formula. But in this class, we are not going to discuss it further. But all you have to know is the concept. The uncertainty basically uh, tell us the characteristic of dispersion value or the including the error, including the accuracy. Uh, so we are usually we use or we calculate the standard deviation to as the uncertainty of a measurement or certainty of a device. Then traceability. Okay, this you have to remember. There's no option. You have to remember what is traceability chain. Okay, traceability chain okay, represented by this figure. Okay, so remember that this pyramid represent the uncertainty. Okay? The uncertainty. By definition, what is uncertainty? By, by definition, you can find the definition. Uncertainty is an unbroken link comparison uh, of measurement. Unbroken comparison of measurement uh, with stated uncertainty at every level. Okay? Meaning that, okay, we have, okay, this is an example, tier of measurement. Tier of measurement. We are basically at the bottom. Okay, at the bottom, end user. Like this device. Okay, this device, uh, temperature device. So this is our tool. So this is our measurement. So end user. This is our end user device. Okay? So the uncertainty level of this device, okay, by standard, has the highest value, highest value, uncertainty. Meaning that the accuracy is the lowest but acceptable. Okay, lowest, but is if we compare to other measurement standard. Okay, so as you can see from the pyramid here, pyramid, the uncertainty is it has the biggest volume of uncertainty. Okay, so the plus minus or the accuracy or the error is bigger as compared to the other measurement standard. Okay. Then if we move forward, okay, industrial standard, okay, enterprise in the industry, they have their own temperature measuring device. Like for example, we have discussed about thermocouple. Okay, thermocouple, we have other more accurate device. Okay, so of course they have more accurate device, which have a lower amount of uncertainty. Okay, the amount of uncertainty as compared to the end user. But okay, our device, we can use the industrial device, okay, to calibrate our device. We can use to calibrate our device. Let's say we set in an experiment a temperature of a body. We set it as 25 degree Celsius. Then we take the device from enterprise, and then also we compare with our device. Okay, let's say this device. So we look at the difference between the device. Okay, so if our device have some offset, so we calibrate. We adjust the deviation or the error so that the output will be uh, as same as the what we can get from the enterprise. Okay, and there are higher measurement standard. Okay, we have like the calibration lab. Okay, and then in the level of state or country, the highest will be the National Meteorology Institute. Okay, but in the world, the highest will be the BIPM or the International Body of International Standard. Okay, in France. So basically, they keep the instrument or the instrument that define the basic unit. For example, weight. Okay, weight. They keep the device or the object that defined as 1 kilogram. Okay, 1 kilogram is defined as a metal, okay, alloy metal, iridium, platinum. Okay, uh, shaped as a cylinder, have a certain dimension. I think it's it has a diameter of 68 millimeter, height 68 millimeter, and then kept somewhere in the institute. So that is used as an international standard of 1 kilogram. So this standard will keep on evolving. Uh, so the definition will keep on improving. So for example, weight, if we use the metal, so maybe at a certain time there will be some corrosion. So there will be some characteristic decay, but that will only happen in a 1,000 year or maybe in a million year. So this definition they can move on into non-physical quantum quantum formula and so on. Right. I think that is all that I want to share. Okay, for maybe if you have any question about your own revision for your test, you can always drop the question using the WhatsApp. So maybe you can use the group or individually. Okay. So with that, there's a question: formula quantity in exam or formula you have to memorize. Okay? You have to memorize the formula. Okay? But we understand. Okay, some formula takes time to derive. So usually we do not, like for example, we will give the force equation or work equation. Basically, we expect you to already know what is force, what is work, right? Force, like for example, equivalent to mass multiply with acceleration, right? So and then acceleration is what uh, different of velocity over time. What is velocity is distance over time. So basically, you can derive from the beginning from scratch. But we know the time constraint. So we usually put uh, certain dimension for certain unit, so that you don't waste your time or you use your time a lot of your time to derive the equation from the beginning lah. Okay. Right. So with that, I conclude my class. So uh, remember to fill the equation. Remember to fill the online form for declaration. And please be prepared. Okay, before 10 a.m. this Saturday. Okay. If you have problem, let me know early. So far, I checked. No one has the problem to for test one. Okay? If we have I have put the effort to make the WhatsApp group, and I hope each individual play your role. So basically, we are in a trial and error time lah. We have to do whatever we can to complete your course. Okay. With that, I say thank you. I think the test one will be carried out. Yeah, you have to download. We will set a question, and then you have to maybe download, or we will look later. You have to download the question, and you have to answer within specified time, and then you have to re-upload. Okay? You have to re-upload to the e-learning. I think you have done it for other classes. You have done a few times for other classes. So I think we also will do the same lah for our class. Okay. Okay, thank you everyone. No, it's not objective. I'm not sure. Frankly, I'm not sure. It's not. maybe negative or negative. I think we have no problem to answer.